In this video, we're going to begin taking a look at the MPLS VPN overview. This is going to take what we talked about in the introductory video of, basically what MPLS is and the reason why it was created, take a little bit more detail. So first and foremost, we're going to talk about what is MPLS. Well, first and foremost, MPLS stands for Multi-Protocol Label Switching. So this was this is the open standards version of what Cisco originally created, known as tag switching. So for those of you that are familiar with the concept of frame relay DLCIs or DLCs, or VLAN IDs or VIDs, or VLAN tagging, the same kind of logic works here, where at layer 2, well, technically layer 2.5, because it sits after the layer 2 header but before the layer 3 header, we are taking and injecting a new header that any router that's enabled to run MPLS will be able to take the incoming frame, look at it, see the label, and then be able to forward based off that. MPLS was originally developed to optimize the forwarding in a service provider, because the logic is the less de-encapsulation I have to do, the faster I can process the traffic. So if I have to de-encapsulate to layer 3, so I have to receive the traffic in, I have to pop the layer 2 header, I have to dig into the layer 3 header, I have to do a routing table lookup, I have to figure out the outgoing interface, I have to switch between the interfaces, rebuild the layer 2 header, and forward it on its way. Well, all of that takes time and CPU cycles. On older devices, before fast switching and Cisco Express Forwarding, or CEF, was a mainstream technology, where fast switching was deprecated in 12.4.20. CEF has been around for almost 2 decades now. Came out, I believe, in the late 90s, early 2000s, and has been the forwarding mechanism of routers at layer 3 now for a long time. Layer 3 switches also leverage CEF, and it's a layer 3 technology, so it won't work if you don't have IP routing enabled. So if you go to a flat layer 2 switch and you type in show IP CEF, you're not going to get any outputs. So it's one of those things where if you have layer 3 routing enabled and you typed in IP CEF, or if you have IPv6 enabled, you type in IPv6 CEF, then you know it's working layer 3 wise. So if you take and originally it was TDP, the Tag Distribution Protocol. Well, not every service provider, not every company runs Cisco. It's a fact. There are companies out there that run nothing but Juniper or nothing but HP. I've actually done a lot of work on HP devices, not so much on Juniper. But not every company runs Cisco. So, but to be able to leverage the technology and the capability that MPLS enables, Cisco came out, or the standards body came out with RFC 3031, which is multi-protocol label switching. Now, the interesting thing about MPLS is it's actually broken up into 2 separate parts. You have the multi-protocol aspect of it and the label switching. So the multi-protocol aspect of it is it can transport different payloads. It's payload agnostic, meaning I don't care if it's layer 2, layer 3, or some other type of capability. I don't really care, because what you're doing is you're removing any dependency on the transport. Now, to be fair, one of the things that we have to understand about MPLS and what it's doing is, it's actually kind of funny. I've worked with a lot of customers over the years, and one of the common things that I see in like job descriptions and working for Cisco partners, I've seen where they've talked about this in the past, where they would like to have somebody that's familiar with MPLS. And I asked the question, I'm like, okay, do you run MPLS in your core? Or do you have MPLS VPN service through a service provider? And I asked the question both ways, because it could be both. It could be just in their core. They could be running MPLS or buying MPLS service from a service provider and then gaining the access to the service that way. So MPLS itself is a way of taking traffic from the customer once it gets to the service provider's edge and then forwarding it through the network. Now, to be clear, MPLS exists only inside of the service provider core. So there are mechanisms, and we'll talk about this when we get into inter-autonomous system VPN. There are mechanisms that will allow us to take and extend layer 3 VPN and layer 2 VPN for that matter in between autonomous systems, which means in between service providers. So if if you have an AT&T and you have a Time Warner Cable and they both have MPLS backbones and they want to talk to each other and exchange MPLS VPN, they can do that. It's a supported technology. We'll talk about that in the inter-autonomous system section. That's one of the options that's available. MPLS itself is actually is leveraged inside the service provider, which means that some sort of transport between the customer's location and the service provider edge at some point of presence or some POP location where a provider edge router sits. Between that, what they refer to commonly as the last mile, that's not MPLS. That could be IP, it could be Ethernet, it could be frame relay, it could be ATM, PPP, HDLC, IPv6, IPv4. It could be the cat's meow. I really don't care what it is. It somehow has to get from the customer's location to the service provider's location, and at that point, it is MPLS. So, as it's forwarded through the network, it's actually dropped off to the remote site or the remote side of the provider's network via MPLS. It's label switched. So that's just one of the examples. The label switching component of it switches traffic between interfaces based on a locally significant label value. So it's similar to a frame relay DLCI or DELCI or an ATM VPI VCI pair. The idea and logic here is if I am bringing this traffic in, what ends up happening is at layer 2, okay, if you take a layer 2 header and you take a layer 3 header, you were to split them in two, and you were to inject the MPLS header, the 20 byte header, and you take this value, and inside of this value you've got a VPN label, you've got a transport label, you have some QoS bits, what they refer to as the experimental bits. You have a bottom of stack bit, which tells you you have reached the very bottom of the stack, and the next hop should be IP forwarded. You get this data, you inject it into the packet, and you forward it on its way. Now, because it's more overhead, you're going to have to account for the additional header space by dealing with some MTU. And we're going to talk about MTU issues that you could see inside the service provider network and how to work around those, but that'll be a video that we talk about down the road. Now, why would you use MPLS? Well, this is a basically transparent tunneling over the service provider network. So if I'm a service provider, typically what's going to happen is in a BGP deployment, you're going to have to run every router that's going to be running BGP is going to have a full picture, full visibility of the entire network, right? So that works, it gets the job done, but that means that inside the service provider core, they're going to have a bunch of BGP routes. Okay, not ideal in most cases, but if it's the internet routers, they're really not going to care. But at the same point in time, it's not exactly the greatest idea in the world to have. Where with MPLS, you're trying to get away from this by using what they call the BGP-free core. So what I'm doing is I'm running IGP in the core, provider edge to provider core to provider edge. I'm doing that in the network so that I can get reachability to where I need it to be inside the core, but I'm not running BGP in the core. I am deploying BGP only on the edge. Now, for clarity's sake, you might be connecting a provider edge router to a provider core router, and that provider core router might be a route reflector or a group of route reflectors that are in a cluster list for failover capabilities. If that's the case, that's fine, but that particular router is simply acting as a control plane reflector. It's simply taking the BGP routes learned in from the customer, regardless of what the customer's PE to CE routing protocol is. It could be BGP, it could be OSPF, it could be static routes. It really doesn't make much of a difference. I take any information that I've learned from the provider, from the customer, and VPN v4 unicast is used to propagate the information from the incoming provider edge router or the ingress to the egress provider edge router, and away you go. LDP is used to get the traffic from ingress PE to egress PE, and that relies on IGP, which is why we needed an IGP in the core to make this work. So IGP is required to get it up and running. Then you run LDP on top of that, which LDP leverages the loop-free topology that IGP builds. Once that's been built and labels have been exchanged and everybody knows who everybody else is, and you have a loop-free path from ingress PE to egress PE, you're good to go. Now, for the sake of argument, LDP is not the only way of getting this job done. I could leverage BGP, I could leverage RSVP traffic engineering tunnels. We're going to talk about how that works. And what's actually really cool about this is if I have RSVP injected into the network, so I'm using MPLS traffic engineering tunnels, those, and I've set the network up to use the TE tunnels to forward the traffic. Those are a different set of labels than what LDP is going to associate. So I could run RSVP TE inside the service provider core and turn off LDP. So not run LDP at all, and strictly use the RSVP TE labels that are allocated through the reservation process of traffic engineering. That is supported. I've tested that out. It does work, because if you're not using LDP for label propagation, but you're using RSVP TE to get the labels to propagate, why keep TE enabled or LDP enabled? You can disable it. So what you're ultimately trying to do isn't necessarily trying to get the label values to work. What you're doing is you're enabling higher level services like layer 2 and layer 3 VPN. So instead of me having to go and use some sort of overlay tunnel like a DMVPN or something else, I can route with the provider, not route over the provider. So let's talk about that for a minute. What does that mean, route over the provider versus route with the provider? So if I'm going to do some sort of GRE tunneling, OTV tunneling, VXLAN tunneling, IP and IP, I really don't care what tunnel term you use or what tunnel encapsulation you leverage. If you are trying to hide the infrastructure that sits between your local tunnel endpoint and the remote tunnel endpoint, then you're overlay routing. You're overlay tunneling, which means the infrastructure sitting between those two tunnel endpoints is hidden from the trace route. So if I do a GRE tunnel between two routers and I encrypt that with IPsec, so I do GRE over IPsec, but it's 60 hops between the two GRE endpoints, those 60 hops look like one, and that's just the GRE tunnel. That's what they refer to as routing over the provider, whereas MPLS you route with the provider. You peer with the provider, you send the traffic to the provider, and you see all the hops in between. And then you end up getting to the other side of the provider's network, and then you get dropped off and away you go. That is what they refer to as routing with the provider, not routing over the provider. Now, there are some mechanisms like traffic engineering that can be leveraged to use underutilized links You can give bandwidth guarantees. You can specify that a particular type of traffic is preferred this path over this path. You could say if it matches this particular value, you can't take this path through the network. We're going to get into traffic engineering in its own dedicated section, which will be called MPLS TE. Take a look at that, and we'll dig into the details of that, because that's going to be its own dedicated section, because there's a lot to go over. Same thing with like segment routing and inter-autonomous system VPN and layer 2 VPN and multicast VPN. Those will all be dedicated sections that you're going to be able to go and watch and stuff like that. Now, the other thing too here is the detect and repair failures. MPLS TE Fast Reroute is a very popular feature, which basically allows me to route around failures in the service provider core, whether they are link-based or if they are node-based, whether it's next hop or next hop. And we'll talk about that as well. So the MPLS label format is definitely necessary to understand, and we'll get into some Wireshark captures to see exactly how this looks. But this is specified in MPLS label stack encoding, which is RFC 3032, where you have a 4-byte header. And I apologize, I was incorrect earlier. It's actually a 4-byte header, not a 20-bit. I was thinking, I said I forget the exact term that I used, but it's actually a 4-byte header, not a 20-byte header. There is a 20-bit label that is associated. There's a 3 bits of experimental, and then you get experimental. This is what your quality of service is going to get mapped to. So by default, if you are marking any of your traffic on the customer side and you send traffic to the provider, by default, whatever the class of service or type of service markings are in the packet are going to be automatically copied to the experimental bits in the MPLS header and sent across the wire. And then you get a S bit, which defines the last label in the label stack, and then you get an 8-bit TTL. Whenever you send traffic to the MPLS, whatever TTL value was received by the provider edge router from the customer, that number is then copied into the TTL value of the MPLS header. And then as you traverse the network, every hop you decrement, and then when you reach the remote end, you forward traffic on as usual. So when we talk about this, you'll see the bottom of stack bit. This is usually, well, we'll see this when we actually talk about PHP and how that works. The logic here is with the bottom of stack bit is you have a 2-label stack by default. You have a transport label and you have a VPN label. The transport label is allocated through RSVP-TE, BGP labeled unicast, and label distribution protocol. The VPN label is actually allocated through BGP VPN v4, which is why the provider edge routers, whether in a full mesh configuration or appearing to a route reflector that will talk to other PE routers, when you receive traffic in from the customer, and regardless of what the PE to CE routing protocol is, if it's BGP, you don't have to do anything. Because it's the same protocol, just 2 different address families. It brings that traffic in, and then it simply copies the information from the IPv4 unicast or IPv6 unicast address family, and it copies that information into the VPN v4 or VPN v6 address family, and then it propagates it to wherever it's got to go on the remote end. Now the cool thing about that is whenever you have a new route, if you look at it, you're going to see the label associated. VPN v4 BGP is where the VPN label, the customer route, whatever the customer advertises to you, a label value is associated to that particular value, whatever that prefix is, and then that label value does not change. So if I was to go into any given router and look at the details of a particular VPN route learned from the customer, I'm going to see a VPN label associated. And then if I was to go and do a hop-by-hop trace of the network and say, okay, where do I got to go to get from the ingress PE to the egress PE? That's what they refer to as the transport label, and that is allocated again through either BGP assigned labels, RSVP-TE, or LDP. Or static labeling if you want to go that far. We're going to talk about that as well down the road. Those are all very useful capabilities that you can leverage in order to get the traffic from point A to point B. But that's inside the service provider core. That is how the provider is going to look at how to transfer your traffic from the ingress PE router to the egress PE router. And that is how that is built. When you get to the router that is directly connected to the provider edge router, that is the exit point for your label switch path. The label switch path is going to be the label switch routers that you must traverse, or your traffic must traverse, go across and go through to get from the ingress PE router to the egress PE router. Wherever that label switch path or that LSP terminates, the hop before that is where the bottom stack bit is going to be present. If it is set to a 1, it means it's the very bottom label. If it's set to 0, that means there's still 2 labels in the stack. If you get to the router that is the last router before the provider edge, that is what they refer to as the penultimate hop pop, or the PHP. It's the next to last. So what ends up happening through the label swap, label pop, label push, pop, and labels push, swap, and pop operation is when traffic comes in on the provider edge router, the ingress PE, a label is pushed, and then as that packet, I should say, traverses through the service provider core, on a per hop basis, that label is swapped to another label on a per interface basis. And I will walk you guys through an actual flow of MPLS of how that comes into play. And then as that traffic reaches the router that is the provider core router that is directly connected to the PE that you're going to use to lead to get to the destination you're trying to reach, that is the next to last hop. So what ends up happening is the transport label is actually popped from the data packet, or the data plane and the control plane, and then what ends up happening at that point is you look at that data, and when the traffic comes in, if the PHP router says pop, you are not going to do any forwarding based off of layer 2. You have to do the forwarding off of layer 3. So then you look in the routing table and say, okay, where am I trying to go? If you're trying to go to this next hop IP, you have to do a recursion to the routing table, and it says, okay, well, I know I'm going to this particular IP address, forwarded via the routing information base, or the RIB. That's what ends up happening, and as the traffic hits the provider edge router that's the egress PE, then what ends up happening is you get a label pop for the VPN label. It's stripped off, and then the native IP packet is then forwarded through the network. What you're basically doing with MPLS, with the label values, is you're actually going in and just encapsulating the traffic from the ingress PE to the egress PE with a different type of encapsulation. You're saying LDP versus GRE, or IP and IP, or OTB, or pick an encapsulation that you could use, VXLAN, and you're forwarding it via LDP. It's just an encapsulation because you're adding another header. It's no different than GRE. GRE does the exact same thing. So does VXLAN. All you're doing is encapsulating it with a different protocol. That is it. So how the labels work is MPLS labels are bound to a FEC, or a forward equivalency class, which is IPv4 prefix for our purposes. So what that really means is you take a group of packets that are going to the same destination, and they are then being forwarded to the same destination. They're in the same forward equivalency class. There's multiple FECs you can leverage, because you can have multiple destinations in your network, but they might be IPv4 prefixes. If you have an IPv4 prefix that was learned from a remote PE router, then its FEC, or forward equivalency class, maps you to the destination PE router that advertised that particular IPv4 prefix to you. And that's the key factor here. So when you look in the show MPLS forwarding table for a particular prefix, and you see the values, what you're actually looking at is the forward equivalency class. It knows how to get you from the ingress PE to the egress PE based off of the information that was propagated from the remote end. Now, a router uses MPLS label forwarding information base instead of the IP routing table to switch traffic. Now, one of the key things here that I want you guys to understand is it's not traffic comes in on the router and then it's immediately jumps to the MPLS. That is not the case. What it actually does is there's a layer 3 lookup, and then it's pointed towards the label forwarding information base. That's what ends up happening. So there's a layer 3 lookup first, and then you start switching via MPLS. That is how it works. Because then you got to figure out what the out. Do I have a next hop? What is it? It's a label value. So then you push the label, and then once the label is pushed, then you forward it based off of the LDP database. And as you get traffic through the network, that's basically how you associate it. The switching logic is if traffic comes in on interface 1 with a label of X, you send it out interface 2 with a label of Y. So the logic is like this. Every router uses what they refer to as a label space. The label space, there's technically two of them. You have the platform wide and you have the interface specific. The platform wide is used by most Cisco routers where all the interfaces of the router are pulling from the same label distribution protocol label pool. So think about kind of like a pool of IP addresses. Instead of IPs, you're mapping labels. Well, the label space is always 0, so it's always going to be there's an identifier. It's a 6-byte identifier. The 6-byte identifier is going to identify the router that advertised you the label values, and then the :0. Excuse me. :0 always means that it's platform wide. ATM is the only interface, at least that I'm aware of, based off of reading documentation and other research, that only the ATM capable line cards that support interface specific label values, label spaces, will use that. So I would say that the only way that labels are allocated is through the platform wide, and you can't specify label spaces or a label range at the interface level on any Cisco router I've ever touched. It's always been a global configuration, which means it's platform wide. You can dictate the label range that MPLS will hand out to VPN learned routes, and you can specify the dynamically allocated range and a statically allocated range, so that when you're doing static label values and stuff like that, you could go through and create static LSPs for specific traffic. You can do that. So what you might see in a non-specifically associated label value range, so meaning if you don't specify a label range, the router is going to allocate labels for traffic via LDP, not VPN v4, or not VPN, but LDP for the transport label. You could see the same label you use multiple times on multiple hops. That does not mean that there's a problem. That just simply meant that for any traffic destined to that IP address, the router automatically allocated that particular label value for that particular prefix. Because you have to understand that when you're dealing with transport between provider ingress PE and egress PE, you're using LDP, and if you didn't specify the beginning and ending range for the dynamically allocated labels, then it's going to start off using the very beginning of the range and work its way up numerically. So the very beginning label value is 16 on iOS and 24,000 on iOS XR. You can dictate those differently if you'd like, but that's where they start. So if I have an inbound packet coming in on interface 1, what I'm going to do is I'm going to look it up and I go, okay, I know that I have to do a routing table lookup to figure out what the next hop what interface I'm going to use to get to that particular next hop IP address is. I'm going to go in and take a look at the routing table. The routing table is going to tell me the outgoing interface. I look at the MPL, and in the routing table it's going to say label value X. And then what you can do is you can dig in to the label information base, and it's going to say, okay, if you receive label 22 coming in, you're going to swap it for label 63, and it's going to go out towards gig 2.1 and then forward it on its merry way. That's basically how it's going to look, and I'm going to show you what that looks like in an upcoming video. I'm actually going to walk you through I've got an intra AS VPN set up already, and you guys will be able to see. I'll walk you guys through the step-by-step recursion process, because that's really important to understand as you're going along here. But that's one of those things where as you're going through, if you know how to look at how the logic of the recursion works, it'd be really easy to determine which way traffic is going. Now, you've heard me mention a few different devices, so let's go ahead and actually define some of these device roles. So you have the customer edge, which is the customer's device, which customer's location is probably a better way of identifying it and defining it, because I have found that having worked with service providers for years now, both as an engineer and as a consultant, I have found that with customer edge, just simply means that it's the edge of the customer's network. Nothing more than that, really. Whether it's managed services, whether the provider manages the router or the customer manages the router, is irrelevant. Then you have the provider edge router. This is the edge of the network, and the provider core. So CE devices are customer edge, last hop device in customer's network before it hits the MPLS cloud, and it connects to the provider's network, and it can be layer 2 only or layer 3 aware. So I can have a point-to-point connection via MPLS and have it just basically extending VLANs between two sites. I could be using a router and terminating the label switch path on my local router, doing some sort of layer 2 VPN between the two sites, so that two switches look like they're directly connected even though they're not. Or layer 3, which is what we're going to be talking about out of the gate, which is going to be the layer 3 VPN. Typically, these are not MPLS aware. They are strictly IP based. Then you get the PE device. So this is the provider edge, or sometimes referred to as the label edge router. You might hear me refer to that, where these guys are the last hop device in the provider's network. So the provider edge is definable between what it connects to. If it connects to a customer and a provider core, it's a provider edge, or the PE. A PE performs both IP routing and MPLS lookups, and for traffic from customer to care, receives unlabeled packets from via IPv4 and adds one or more label values to that particular packet, and forwards packet into the core via the label values associated. So it says one or more label values. Well, one of the things you could end up happening, what could end up happening in an environment where you've got MPLS deployed, if you just use LDP, you're going to see a 2-label stack. One transport label, one VPN label. That's it. You use a transport label to get from the ingress PE to the egress PE, and then the VPN label to get for you from the, or I should say, the transport label is going to get you to, is going to point you towards the egress PE, but is going to be popped one hop before that. So there are some issues in the network where, there are some situations where if you don't do it right, you could pop one hop too soon and black hole traffic. So we'll talk about how that works as well. That can be a bad day. But normally it's going to be a transport label to get you to the PE router, and then the VPN label is going to identify the outgoing interface for you, where you might have one or more labels. So for instance, if I'm using MPLS traffic engineering, I could have a provider edge to LSP, not a end-to-end, but I could do a RSVP TE tunnel associated label to a certain point in the network, and then from that point in the network to the provider edge that is the egress as LDP, which means I'm going to see a three label stack. I'm going to see a label to get me to that provider edge, provider core device. That label is going to get popped, and it's going to be an LDP to get me to where I've got to go. So there's multiple ways of looking at it. We're going to take a look at that when we get into TE tunneling. There's a lot to it, a lot of individual components, but that's one of the things that's actually really cool about TE is it does give you a lot of flexibility. It's just there's a lot of details that need to be understood about it. So from the traffic, for traffic from core to the customer, you end up receiving MPLS labeled packets, and it removes one or more MPLS labels and forwards packets to the customer. That's what a PE device does. It sits between the border of the provider core and the customer edge. Now, the provider devices, or the P devices, is the provider core, previously known as the label switch router. So you'll still hear me refer to it as an LSR. An LSR is a PE router, and LER is a provider edge. This is the core device inside of the provider's network, and it connects to PEs and other provider core routers with no customers. And this is switches based only on MPLS label. So what are some of the device operations? PE and P routers perform three major MPLS operations. There's a label push, which adds a label to an incoming packet, or what's referred to as the label imposition process. So it takes an incoming raw IPv4 packet and it injects the 4-byte LDP header, MPLS header to the packet. Then on the label switch routers, so label push happens on the LER, the label edge router. The label swap, or the label LSR, label switching router, replaces the label on an incoming packet. So it receives it in and then swaps it for another one. This is referred to as the swap operation. And then you have the label pop, which removes the label from an outgoing packet, and it's referred to as label disposition. This is where you're at the penultimate pop, or the next to last router in the label switch path. You pop the transport label, pass the traffic onto the provider edge via with the VPN label. It receives that and knows where to send it. Now, label distribution itself, labels are advertised via a label distribution protocol, which is referred to as LDP, which advertises labels for IGP learned routes. So LDP is going to get you between your provider edge routers. That's all it's supposed to do. Now, RFC 5036 is what defines it. There's LDP, there is multi-protocol BGP, where I can say send label in a neighbor statement. So if I have a situation where I don't want to run LDP in the core, but I've got IPv4 up and running, I want to go and I want to run BGP labels only, I can do that too. So BGP VPN-v4 can allocate the VPN label, but I can also do a send label where I'm going to use BGP labels for recursion and transit inside the service provider core. Then you have RSVP traffic engineering, or RSVP TE, which is RFC 3209, where you actually go in and you create a MPLS specific tunnel between the provider in the provider core, because it's not just PE to PE, it's PE to P, P to P, P to PE, lots of different variations. We'll take a look at exactly how each one of those goes through as we get through the rest of the course. But these are the ways that you can distribute labels throughout the core. We're going to take a look at each one. The label distribution protocol is the easiest of them all with how easy it is to get working. We'll take a look at BGP labels in an upcoming video, and then RSVP-TE label later on. Now, label distribution protocol specifically automatically discovers neighbors with a hello protocol. And the hello protocol is actually going to use multicast UDP to 224.0.0.2 or the all routers multicast. So it uses the source and destination port 646. So it's not an IP protocol. It's using the same mechanism as HSRP to figure out who's peered to, just to use a different port to communicate. So this is a way for it to discover directly connected neighbors. And I specify directly connected because LDP supports both local directly connected neighbor adjacencies as well as remote targeted LDP sessions, which is basically how RSBTE comes into play. And we'll talk about that later on. So when we get into things like LDP session protection, this is a mechanism that we can leverage. So the hello includes the IPv4 transport address, and the address to use for the TCP session, and it defaults to the LDP router ID, and it's a point-to-point TCP pairing. So what's actually really cool about this is LDP itself uses UDP port 646 to find and discover and form adjacencies with directly connected LDP speakers. It also uses TCP port 646 for actual label exchange. So once the routers find each other and learn about each other, then what ends up happening is they go through, form an adjacency with each other, which you guys did see, and then once it does that, it then exchanges label information through TCP. So there's some advanced capabilities that you can do in authentication, and you can do filtering and stuff like that based off this information, and use some fancy dancy tricks to filter out what label values you learn from who and where and all that good stuff. I have some videos that we're going to be doing where we talk about filtering and stuff like that. The filtering can get kind of advanced, so we're going to be definitely talking about those individually as we go through. Now, its job is explicit to its name. So LDP distributes labels throughout the SP core via IGP reachability. The labels it is distributing are used for the transport label in the MPLS 2 label stack. The two labels used are the transport label and the VPN label. The transport label can change on a per hop basis and points to a remote PE loopback address. The remote PE loopback address is the end of a label switch path or an LSP, and the VPN label is actually allocated from VPN v4 BGP when a PE learns from a CE, and that'll be marked with a V in the MPLS forwarding table, and you'll see what that looks like once we actually go through and take a look at it. Now, forming LDP adjacencies. LDP sessions are formed reliably over TCP. This is after you've discovered your adjacency. Unicast between the transport addresses is TCP 646, and this implies peers must have routes to each other's transport address. These loopbacks that we keep referring to, these must be routed. So unlike OSPF's advertising router or router ID, which is just an identifier, where if you get into like things like the forward address in external OSPF and things like that, where you want to change the actual next hop you route towards, then the advertising router needs to be reachable. In this case here, if you don't have a loopback advertised into IGP, LDP will never work. It's just never going to happen. Now, the transport address could be modified but not normally needed. So for instance, I could change the transport address to not be the loopback, but to be a direct connected interface. Depending on the implementation, you might have a firewall that requires that. ASAs don't support loopbacks, so you could change the transport address to be the interface, and the ASA will be able to reach that. Now, when it comes to advertising labels itself, once LDP sessions are established, label is advertised for a FEC. So a label to IPv4 prefix mapping and a route and label number binding. So label distribution can be implicit or explicit. So unsolicited downstream versus downstream on demand. And it implies that it depends on the implementation and the configuration options. Now, downstream on demand, or DoD, this is only for label controlled ATM interfaces, where the LSR sends a request for a label binding for a given routed path, and the FEC or forward equivalency class identifies a group of packets heading the same direction or going to the same destination, and the label information base or the label information base or the lib will only have one remote binding. The FEC binding is one for one and from its downstream neighbor, which means it's specific. So I'm asking for the actual information that I need and not unsolicited downstream, which means that I am going to advertise everything. This is supported on all interfaces except for label controlled ATM. This is what they refer to as unsolicited downstream. This is what we will be running, is unsolicited downstream, because basically it's similar to Ethernet flood and learn, where every LSR will send all of its label bindings for all IGP routes to every directly attached label switch router automatically. There is no request sent from the LSR to send a label switch update from a neighbor. The label information base will show a label binding for each of its neighbors, and once an LDP label switch router has discovered another LSR, they form an adjacency and exchange LDP info. Now there are a couple of retention modes. We have the LLR, or the liberal label retention, where all the labels learned by adjacency neighbors are stored in the lib for a given FEC, and the label that points to the downstream LSR based off the fib is installed in the LFib. Since only one label is used, the other labels are used for backup and enables fast reroute. Conservative label retention, or LLR or CLR, is only supported on label controlled ATM interfaces, and only the label that is stored in the lib is the label from the downstream LSR. So just like downstream on demand, this is how what labels you actually maintain. There are some LSP control modes as well. We have independent, where every LSR in the SP core will bind a label to IP mapping or FEC based on the IGP or MPLS TE or segment routed tables. Each LSR has its own view of the SP core, but relies on the underlying loop-free routing to determine the outgoing label. So LDP itself is going to leverage whatever IGP forwarding it tells it to do. Where RSVP-TE, I can go in and modify that value using the TE metric, and I can specify a different forwarding mechanism that's going to override IGP. So if IGP says use a 7-hop path, which is the shortest for the IGP, the IGP doesn't have visibility into the network the way that RSVP-TE does through the CBR, constraint-based routing. It doesn't know about the contention in the network. So if TE or RSVP detects that the constraints cannot be met based off of a given path, it can choose a different way to go, which might be better than the IGP path. Even though the IGP path might have higher bandwidth links, if they're overutilized, and a lower value link, like 100 meg versus a gigabit, is barely getting used, the traffic is going to get forwarded over the 100 meg link, not the gigabit. Then you have ordered, so only supported on ATM switches. So you can pause the video and read that last two lines. So there are a couple different types of neighbors. You have the local one, which is what we've got default set up, or that we do by default. And so this is how IGP works as well. So neighbors are discovered via link local multicast to the all routers multicast group 224002. This is only for directly connected LSRs that detect another LSR. So you are going to send hellos to 224002. If you get a response, which is going to be an interface IP address, then you know that's another label switch router, and then you guys begin doing the happy dance and exchange labels and all that good stuff. The LSRs won't form an adjacency by default unless they can determine the loopback is being advertised, which is why I mentioned that if you don't enable it, then in IGP you'll never receive labels. It's not if it's not, then the loopback interface needs to be advertised. Needs to be IGP enabled, the transport interface needs to be changed. Once the neighbors have formed an LDP adjacency, they will begin exchanging the label information. and Neighbor Discovery uses UDP port 646. Label Exchange uses TCP port 646 via unicast, and once the label values have been exchanged, you will then begin forwarding traffic like that. You'll find that typically IGP will converge before LDP does, and there are some caveats with that, where if LDP has not converged but IGP has, then that could be a bad day. You can start black holing traffic and whatnot. So we'll talk about this when we get into things like session protection and synchronization, but it's a big deal in synchronization to make sure that whatever you're advertising, as long as IGP and LDP have to be synchronized and they have to be converged at the same time. Now there is a remote way of neighboring where this is for LSRs that are not directly connected and need to form a multi-hop LDP adjacency. This is referred to as a targeted LDP or a TLDP adjacency, and uses unicast TCP connections between the LSRs to form the adjacency. This is typically the method used by MPLS traffic engineering, and one LSR is configured to form a targeted adjacency, and another LSR is configured to listen for the targeted hellos, where by default targeted hellos are dropped. So if I have a router that's trying to form a targeted LDP session with another one, I have to allow the targeted hellos inbound. When it comes to advertising labels, labels could be advertised for some or all of the routes. So Cisco by default uses all routes when you really only need the /32s for the remote PE /32 loopbacks. You can specify a label range, so you could use MPLS label range value, beginning value, ending value, where the POP label means the destination is directly connected. No label means the destination doesn't have an allocated label assigned. This could be a misconfig or a transport issue. Depending on the situation at hand, that could be a big deal, or it could be exactly what you want. It's really up to what you determine to be acceptable. But if you are not using, you'll see there's a technique known as VCCV, the Virtual Circuit Connectivity Verification Tool, where it's going to basically, if you do away with the loopback, you're going to break the LSP. It's a requirement for that to be there. Now there is a label binding and a space. A binding is an association between a destination prefix and a label. Labels are bound after a label space has been allocated, and the first 16 labels are not allocated to prefixes as they are used for LDP operations between label switch routers. And there are two different label spaces. You have the interface specific, which based on testing and research is not supported on iOS or XR, and is only supported on labels controlled ATM. And then you have platform wide. This is a single platform wide label space that all interfaces use to allocate labels for from learned IGP routes. So when you actually go through and form an adjacency, there's already a default range, and that range is allocated on a per prefix need, incrementing up from low to high, so 16, 17, 18, etc. LDP uses a 6-byte LDP identifier. The first 4 bytes are tied to the LDP router ID, used to identify the LSR in the labeled network. The last 2 bytes is used by the local label space ID. Since only platform-wide is supported, the ID is always 0. So you're going to see whatever the router ID is of the remote device, :0, and this is what is seen on the CLI. So that's basically how you could view it and see exactly what's going on in the network. Until next time, guys, thank you so much for stopping by, and we'll catch you guys in the next video.